Radiation sounds scary, but what is it? Well, radiation is energy. More specifically, energy that travels as waves. Some examples include microwaves, which, while they release non-ionizing radiation, or the visible light spectrum, which are colors, and UV rays from the sun. And we know elements are everywhere, they make up stuff. And elements are made up of smaller parts, they are protons, neutrons and electrons. The number of protons determine the kind of element an atom will be, and each element has a certain amount of neutrons and electrons. But if they're an element that has a different amount of neutrons than normal, those are called isotopes. But why mention the two? Well, we have things that are related to both. They are called radioisotopes. These aren't stable because they contain too much energy, but they reach stability by emitting radiation. And in the process of becoming stable, they can release different particles, such as alpha particles, beta particles, and gamma rays. And sometimes emitting radiation once isn't enough to become stable. This is when decay chains occur. A decay chain is when a radioisotope will decay multiple times to become stable. So for example, this decay chain on the right, it starts with radium, then decays, releasing either alpha or beta particles after a period of time, then finally it reaches stability as lead-206. Let's take a closer look into alpha decay. We write this particle like this, and it's actually just like a helium nucleus, with 2 protons and 2 neutrons, hence 4 at the top, and a charge of 2, as shown at the bottom. Let's take a look at an example of alpha decay. Uranium-238 with a charge of 92 goes through alpha decay. Remember, the top number is the total number of protons and neutrons. We know an alpha particle is emitted. This means the top number in uranium will go down, because uranium loses protons and neutrons to become more stable. In this case, it went down by 4 because that's how many protons and neutrons an alpha particle has. Same thing happens with the charge, it goes down by 2. And remember how elements are distinguished by the number of protons. Well, since we took away 2, now we have a new element. That new element happens to be thorium-234, with a charge of 90. Don't write it like this on a test, write it like this. Write the alpha particle last. Next there is beta decay, this one is a little more complex. This involves converting a neutron into a proton, or vice versa. And there's actually 2 types of beta decay. Beta minus decay and beta plus decay. For beta minus decay, the nucleus turns a neutron into a proton. It also emits an electron, which we call this electron emission, which we write it like this. And to write the electron emitted, it is just like any other element or particle, except a negative charge and nothing for the top number. Let's look at a beta minus decay reaction. Carbon-14 with a charge of 6 decays. We know neutrons turn into protons here, so the top number will remain the same. But there will be a new element since there is a different number of protons. So here, we get nitrogen-14. But take a look at the charge. An electron has been emitted. Because of that, the charge for nitrogen increases. And lastly, we will include the antineutrino emitted. And there aren't numbers beside it because it has no charge and virtually no mass, i.e. no protons or neutrons. Beta plus decay involves the nucleus turning a proton into a neutron. And like beta minus decay, other particles are emitted, in this case a positron. A positron, the antiparticle of an electron. It's like an electron, but it has a positive charge. And we can write this like this, similar to the electron. And lastly, the neutrino. It's another particle emitted during beta plus decay. Let's put this into action. Carbon-11 with a charge of 6 undergoes beta plus decay. Just like beta minus decay, the top number will stay the same. But like beta minus decay, the charge changes due to the emission of a positron. And remember, a proton is becoming a neutron, which means there will be a new element. So we get boron 11. And the charge of boron is 1 lower because of the positron. And then we write out the positron. It's just like an electron but with a positive charge. And add the neutrino as well, no numbers beside it because it is also charged less and almost mass less. Lastly, we have gamma decay. This happens when an element is in an excited state. And it is excited because it has excess energy. That excess energy usually comes from the element undergoing beta or alpha decay beforehand. And it wants to lose energy to become more stable. And how it does that is it loses a high-energy photon, called a gamma ray. Gamma rays have lots of energy, no mass and no charge. And we write gamma rays in the reactions like this. Let's look at an example. Helium-3 with a charge of 2 undergoes gamma decay. And we show it is excited by adding an asterisk. And the result of the decay does not end with a new element. The number of protons is the same, therefore no new element. Ditto with the neutrons, therefore the top number is the same. The charge doesn't change as well because a gamma ray is charged less. And lastly, we add the chargeless and massless gamma ray.